we can call this thing enumerative mirror symmetry, which predicts equivalence of not categories, but some sequences of numbers on both sides. So on the symplectic side, we have chromoitan invariants, which are certain enumerative counts coming from counting curves, geomorphic curves into your symplectic manifold. On the complex side, these are certain invariants associated to variation of complex structures. And the prediction is that mirror symmetry actually allows you to match these two numbers on both sides. So if this homological mirror symmetry, the categorical formulation is supposed to give you something more, you should definitely be able to recover the enumerative mirror symmetry from homological mirror symmetry. And this question, or rather, this program was somehow implicit in Koncevich's original proposal. So one of the ways he indicated was to formulate something like categorical enumerative invariance. So we start with a category which has suitable properties, like those which arise in mirror symmetry, and then we try to construct a categorical version of chromoitan invariants. So called categorical and enumerative invariants. And so basically there are two steps involved in this construction. So the first step is this theorem of Costello. It's quite well-known theorem which gives a topological field theory structure on the Hochschild homology of the category. So again, you'll notice that Costello's theorem assumes that the category is of a certain type, namely it's compact Calabi-Yau. But these are the properties that usually many of the categories that arise in mirror symmetry have. So let's look at what the statement says. It's saying that there are maps from Hochschild homology's kth power to Hochschild homology's lth power, coming from moduli space of coming from the homology classes of moduli space, certain moduli space. So I'll say what the moduli space is. These are moduli spaces of Riemann surfaces with boundaries. So you have Riemann surfaces, you assume that the boundaries are modeled on the complex half plane. And moreover, we assume that these boundaries are framed in the sense that these boundaries come with an analytic S1 parameterization, So that's what the framed in M framed refers to. And why we need this parameterization is basically when we have two surfaces, these parameterizations allow us to take two boundaries and identify them using the respective parameterization. So I mean, it's possible to do it with much less data. Like you don't have to assume analytic parameterization. Maybe it's possible to do it with smooth parameterizations, but just for convenience, we are going to assume that it has an analytic parameterization. So in particular, note that the space is not finite dimensional because the space of parameterization itself is infinite dimensional. So another thing to note here is there's a natural map from these modular spaces of framed bordered Riemann surfaces to the usual Deligne-Mumford compactification of modular spaces. So by usual Deligne-Mumford compactification, I mean the stable nodal curves with k input mark points and L output mark points. So in total, there are k plus L mark points, k of which we designate as input and L of which we designate as output. And the map itself is given by just capping off these boundaries by gluing in disks there and putting mark points at the centers of these disks. Okay, so this is the map from framed Riemann surfaces to the Deligne-Mumford compactification. And what Kontsevich proposed is that under suitable conditions, we should be able to actually extend this map constructed by Costello to the map which are parameterized by homology classes on, in fact, Deligne-Mumford compactification. So in some sense, we are lifting the map given in Costello's statement along the map from frame Riemann surfaces to compactified modular spaces of Riemann surfaces.
I'm sorry, I have a very, very naive question.
Yes.
What is What is H star of C? C is a manifold, or is it a category?
So C is a category.
So it's
C is
C. C. Okay,
compact
sorry.
area of
Okay.
infinity category.
Yeah. Okay, thanks. Sorry.
Yeah, no problem. Right. So the question is, okay. So Konsevich's proposal is when nice circumstances happen, you should be able to extend this map. And once we extend this map, we have somehow maps parameterized by classes, homology classes of Deligne-Mumford spaces, which give you candidate for defining categorical enumerative invariants. That's the general idea of how the invariants are supposed to define. So now the main question is to figure out when such an extension is possible from the framed surfaces to Deligne-Mumford compactification. And so that's the main question we are going to ask: when the first map can be used to induce a map of the second type. The rest of the talk is going to be about understanding some aspects of this question. Okay, so let's turn to. Are there any questions on this part? Okay. So let's turn to looking at what kind of algebraic structures we consider. So we are going to use certain algebraic structures on moduli spaces of Riemann surfaces to make sense of these questions. So the structure we use is called proprads. So if you are familiar with operats are just a generalization of operats where we allow operations which have multiple inputs and multiple outputs. So in operats, you only allow one output, but in proprads, you put no restriction. So by definition, a proprad is going to be a collection of spaces, PKL, one for every pair of integers K and L. And roughly we think of these spaces as spaces of operations which have K inputs and L outputs. So graphically, you can think of it as this kind of corolla that I have drawn here. And these operations are supposed to fit together in compositions. Namely, if you have two operations and you compose some of the outputs of one operation to some of the inputs of the second operation, that's supposed to give you a composition. So whenever you have a way of identifying some outputs to some inputs, you are going to have a composition map as written down here. So that's the structure of proprads, and it should be more or less clear why we are looking at this, because all the modular spaces of Riemann surfaces that I mentioned so far, all of them have this kind of proprad structure. So the first one is this modular spaces of framed Riemann surfaces with parameterized boundaries. And in this case, the spaces of operations with K inputs and L outputs is just, you just put together all Riemann surfaces which have K inputs and L outputs with respect of the genus. So that's the space of operations. And as I said, you can use this parameterization to actually perform the gluing, which in language of this proprad, it corresponds to the composition operation inside the proprad. So this gluing of outputs and inputs of Riemann surfaces is captured in the algebraic structure of proprad. So this is for frame Riemann surfaces. Similarly, you can do same thing for Deligne-Mumford modular spaces. And in this case, the gluing is slightly different. There are no boundaries, but you have these input mark points and output mark points. And the composition is just literally given by concatenating the mark points. That's your proper composition. Okay, so this is some technical part that we need to allow. So for whatever I'm going to discuss later, I'm going to allow some exceptional curves inside the Deligne-Mumford modular spaces. So for example, I'm going to allow genus 0 curves with 2 mark points, and I'm going to declare its modular space to be just a point. So this is just for convenience of stating whatever results I want to say. So in particular, we allow genus 0 curves with 1 input, 1 output, 0 input, 2 outputs, 2 input, 0 output, 0 input, 1 output, and 1 input, 0 output. Okay, that's lots of arrays, but roughly all the unstable modular spaces of genus 0 have added into my collection, just declaring them to be points. Okay. So these were the Riemann surface. These were the examples that we constructed out of Riemann surfaces. So finally, for any space, you can construct an endomorphism properad. So the endomorphism properad, just the operations with k inputs and l outputs is basically all maps from kth power of x to lth power of x, and you have composition defined in a straightforward manner. So why we are interested in properads is basically actions of these properads. And an action of a properad on a space is just defined as a properad map from P into the endomorphism properad. Just like you define representation of a group as a group homomorphism into the endomorphism of a vector space, similarly we define properad action or other representation of properad, or alternatively an algebra over the properad as a map from P into the endomorphism algebra of X. Okay, so this is the central definition that we are going to use. Namely, we are interested in how the properads of Riemann surfaces act on these Hochschild chain complexes. Okay, so this theorem of Costello, I'm just reformulating the theorem of Costello, saying that the moduli, the homology of frame moduli spaces act on the Hochschild homology. And we can restate the question in this language, namely, when you have an action of frame Riemann surfaces, when can you extend that action to an action of Deligne-Mumford, the property of Deligne-Mumford moduli spaces? So you start with moduli space of frame Riemann surface, you have some action on the Hochschild chains, and you ask when can you extend the action to the compactified moduli spaces. Okay, so this is the restatement of what we want to say in terms of the algebraic gadget, namely properad. So are there any questions about this algebraic structure?
Yeah, sorry, I have a question. Are these two homologies of M bar and M framed known? As in, is the homology of M bar bigger than M framed?
Yeah, I mean, the answer is the homologies are not known. So I don't know whether one of them is bigger than other. Yeah, I mean, explicitly, the homologies are not known. Only the genus zero homologies of genus zero modular spaces are known. So yeah, we don't have explicit description of these. Okay, does that answer your question? Okay, I think I'm going to move on. Okay, so let's turn to the next part, which is to describe how Deligne-Mumford compactifications appear from the uncompactified modular space. And this is a statement that's going to actually tell us in what cases you can extend the actions of uncompactified spaces to compactified spaces. So this is the theorem that I want to state. So the theorem is going to be that the Deligne-Mumford properad, so the properad constructed out of Deligne-Mumford compactification, is some homotopy push out of a diagram. So I'm going to say in a minute what the diagram means. So let's just note that the lower left corner of the diagram is the modular space of uncompactified modular, is the properad of uncompactified modular spaces. And we are taking the push out along a map, which takes some subproperad of this properad of frame Riemann surfaces and maps it into a properad constructed out of just points. This is some sort of trivial operad in arities that I have indicated. So let's try to understand what this statement is really saying. So you start with the moduli space of frame Riemann surfaces, and then you consider some subproperad. So the subproperad is basically just consider all Riemann surfaces whose underlying spaces are either annuli or disks. Okay, so the first three things are annuli, and the last two are moduli spaces of disks. So remember, all our Riemann surfaces come with a boundary parameterization. So as a result, all these annuli have an S1 choice of parameterization of boundaries. So you have S1 parameterization on both boundaries. If you rotate both of them, you get the same Riemann surface. So the modular space of Riemann surfaces of the modular space of annuli with choices of this parameterization on both ends, they are homotopy equivalent to circle. So this is for all three modular spaces of annuli, they are homotopy equivalent to circles, and rest of them are just modular spaces of disks with a parameterized boundary, which is just a point. So we notice that we are pushing out along a map which maps all the components to just points. So in particular, it's mapping these S1 families, which are homotopically essential in the modular spaces of annuli, into points. So basically what we are doing is we are taking these S1 families in frame Riemann surfaces and we are trivializing them by mapping them to a point. So that's kind of the content of this push out. Namely, we consider the modular spaces of annuli, which are homotopical equivalent to circles, and we crush them to points. That's what this push out means. And the claim is that if you take the homotopy push out along this map, you actually get the Deligne-Mumford modular space. So remember, we were actually interested in what this means for actions of algebras, actions of Riemann surfaces, actions of the properties. And so here's what it means for actions. So let's say you have an algebra over the frame Riemann surfaces such that you have another map from this trivial property so that this diagram commutes. So what this saying is that you take your action of frame Riemann surfaces and you restrict to these S1 families of operations. And the fact that this map factors to the trivial property is saying that the actions of these S1 families on your algebra are trivial. And so by somehow the universal property of push out, what this is going to say is that if you have such algebra with actions of these S1 families trivial, it actually gives you a map from M bar to end A. In other words, it gives an action of the Deligne-Mumford property on the algebra. And this is what we were looking for, but not quite. So the problem is that this was not an actual push out, but just a homotopy push out. So this is not true on nose, but it's just true up to some higher homotopy coherences. Okay, so let me just mention a few things about the theorem. So the first one is the theorem actually accounts for all higher homotopy coherences, and this is what should be desirable, because when in practice we consider actions of this property. So for example, actions on symplectic cohomology or actions on some Floer theoretic invariants, the actions are only well defined up to some choice of some auxiliary data, which though contractible, it's a choice. And so everything is well defined only up to homotopies. So whatever statements we are going to make, they better be homotopy coherent, and this statement is indeed homotopy coherent. So the second thing to mention is everything is proved at the level of underlying modular spaces and or stacks, not just at level of chains or homology. And what this means is that potentially you could also talk about potentially you could also apply any generalized cohomology theory to this push out and get a push out on the cohomologies of modular spaces with respect to this generalized homology theory. I mean, potentially this has applications to considering maybe Floer theoretic invariants with extraordinary coefficients. Another thing to note is that there have been several results of similar flavor in literature previously, but either all of them were for genus 0, or they only allowed one input. But our result is for all genera, and it allows both multiple inputs and multiple outputs. So that's somehow something novel about the result. And in fact, this fact that you need to allow multiple inputs and multiple outputs is necessary to be able to recover the entire Deligne-Mumford compactification. If you just work with operands, you only recover certain subspace of the compactification given by curves whose underlying dual graphs are trees. But our statement recovers the whole modular space. Okay, so this is just a small comment about some technical point, namely that this is a statement which is stated, at least in the paper, the statement is for something called I/O operadics, which are just small modifications of operadics, but I'm not going to say much more about it now. So is there any question about the statement of the theorem?
Yash, you're already a bit over time, so if you could wrap up quickly, that would be good.
Okay, yeah, I think I'm almost done. So this is the statement of the theorem, and you can, I mean, coming from some motivations from symplectic cohomology, you can actually prove a variant of this theorem where instead of trivializing the annulus with one input, one output, which typically corresponds to BV operator, we actually trivialize something else, namely the annulus with two outputs and no inputs. And this gives rise to some moduli space, which we expect actually recovers some secondary operations. And this is some ongoing work that I'm working on, trying to figure out the algebraic structure on Rabinowi's Floer theory. So this is one instance where just these formal predictions of algebraic structures actually give you some idea of what the algebraic structure has to be in some classical invariants. So I think this is a good place for me to stop. Thank you.
Okay, great. Thank you very much for the talk. Any questions? I mean, we have maybe 3 minutes for questions for the next speaker. Yeah. Claude points out that the Deligne is missing an E in the, it's a typo in the name, but that's okay.
Sorry?
The Deligne, it's with an E in the end. The Deligne-Mumford.
Yeah. Okay.
Anyways, any other comments or questions?
Yes, could you give us a hint of what kind of operation you get on the Rabinowitz-Floer cohomology?
So basically the point is that you are able to get a moduli space where these secondary operations naturally live. So for example, you can look at the secondary coproducts which come from assigning weights to the outputs. And these have natural interpretations in terms of cohomology classes inside this relative group that I've written here. I mean, this is still work in progress. So I can't say that I've verified it, but that's the expectation right now.
But it would correspond to, in a way, to A infinity operations, or to the UK, some UK, for example? I mean,
so could you...
Or not at all? Or not at all?
Could you say that again?
Would they correspond to some I infinity operation?
Well,
or,
I mean...
Or you expect, or it has nothing to do, or you expect something different?
No, I mean, that's definitely, there's something to do here. I mean, maybe you're referring to this IBL infinity structure that exists on positive symplectic cohomology, which is slightly different flavor than Rabinowitz cohomology, because you're quotienting out that, which is much larger. So right now, that's something that I would like to know about, but right now the framework seems very I mean, it seems immediately applicable to the case of Rabinowitz Floer theory, but yeah, I mean, in long term, I'm interested in looking at operations on positive symplectic cohomology, even operations for higher genus and multiple inputs, multiple outputs. This kind of formal statements give you some hints of what kind of definitions to look at.
Okay, thanks.
Okay, I think we don't have much more time for questions. So maybe we can leave it for discussion. So we thank
Sure.
the speaker again. Thank you, Yash. It's a very nice
Thanks
talk.
again for the invitation.